Hello everyone, and thank you for having me here. I'm very excited to share with you some of the research we have been doing at UCSD. Today, I'll talk to you about live programming, about programming by example, and about putting them together in fun and interesting ways. So, let's get started right away. Chapter 1, at first, there was liveness. So live programming is an area of research that has received more and more attention recently. Broadly speaking, live programming is a paradigm in which immediate feedback is provided to the programmer each time the program is modified. This is a relatively broad research area that includes things like audiovisual performances in concert venues. But in this talk, I'll focus more specifically on live programming for general purpose languages. So in this setting, live programming provides a way to immediately visualize the runtime values each time the program is modified. In other words, runtime values always on display. And more specifically, the work I'll be showing you today is based on something called projection boxes, a project we started a few years ago. And the best way to see how projection boxes work is with a demo. Projection boxes are a live programming environment for Python. And to show you how they work, I'm going to implement an average function. So here I have my average function, and to start, I'm going to sum up the elements of the list L. To do that, I'm going to create a variable called s to store the sum. And I'm going to initialize it to 0. And as soon as I do that, I have a box that appears here on the right. And this is called a projection box. And it shows me the value of all the variables at this point. So L is the list 1, 2, 3, 4, because I'm calling average over here with the list 1, 2, 3, 4. And S is equal to 0 because I just assigned S with 0. If I change this statement to be S equal to 10, immediately I'm going to notice that S changed in the projection box. If I put 100, again, I'm going to see that information being changed. So the information is being changed in a live way. Again, as another example, I can change this to a string. And again, the information is going to be updated right away. So let's put this back to 0. So now I'm going to iterate over all the elements of L. And when I do this, I have a projection box over here that appears where every line in this projection box represents an iteration of the loop. So the first column here, the pound column, is just an iteration count. The next one, x, tells me the values of the variables x throughout the loop, 1, 2, 3, 4. L remains unchanged, it's the original list because it's not being modified, and s remains at 0 again because I'm not modifying s yet. Now I'm going to increment s with x, and immediately as soon as I do that, you can see that the value of s throughout the loop gets updated. And here at the very end, if I look what value of s I have that s is 10, which is the sum of the elements of the list. You'll notice this RV over here. RV represents the return value of the function. And in this case, it's equal to 0 because I'm returning 0. The next thing I need now is the length of the list, the number of elements in the list. Now, in Python, there is a function called len that can give me this. But instead, I'm going to do it differently just to show you a little bit more about how projection boxes work. I'm going to create another variable called count, which is going to store the count of the number of elements. So I'm going to start with count equal to 0. And then inside the loop over here, I'm going to increment count by 1. And you'll see that now count gets incremented, and at the end of the loop, if I go over here, count is equal to 4, the number of elements in the loop. And now I can here return s divided by count. And now I can see that the return value is 2.5, which is correct in this case. And the variable k over here, which is the result of the average function, is 2.5. I can now go and change this, the list that average is called with. So I can, for example, put 1, 2, 3, and I can see immediately the result. I can basically put 1, 2, and I can see the result. And I can go through over here and move around and gotta take a look at all the different iterations. Finally, let's say I try the empty list. What's going to happen? Oh, I get a division by 0. That's not surprising. That's because count is equal to 0 over here. Let's say I wanted to handle this. I can insert an if statement here. So if count is equal to 0, I'm going to just return 0. And so now what happens is over here, you can see that the projection box tells me that the return value is 0. And then all the other statements, you can see the statements in the loop here are not executed because in this case, the list L is empty. And this last return statement is also not executed because the function returns on line 8 here with return 0. Now, if I go back to, let's say, having the list 1, 2, 3, I can go back and I can see that now this return statement, s divided by count, is being executed, whereas the return 0 is not executed, and the loop is indeed executed 3 times over here. Okay, so that gave you a sense of how projection boxes work. Before we go forward, I do want to take a slight detour to highlight a few things about projection boxes. So we did a study with programmers, and survey results and interviews show that programmers in our study found projection boxes useful. They were able to not only immediately see their bugs, but they were also able to easily try things out. It's like having an immediate interpreter set up with all the data context right at the point where you program. But I want to focus on specifically one additional aspect that was really important. So one of the really cool things about projection boxes, and in fact, one of the main novelties there, is they actually provide an on-the-fly customizable framework. Although I didn't show the details here, it turns out that there are many knobs on projection boxes that can be tuned to display more or less information. And the knobs can be tuned on the fly very quickly. For example, you can remove certain variables from the projection boxes, or only display the box at the current cursor, or only display a subset of all iterations, or even just hide the projection boxes altogether. This framework is not only expressive enough to capture several prior live programming paradigms from the literature, but it also allows the programmers to switch very quickly and nimbly between them. And this leads us to one of the key takeaways that I would like you to remember about live programming. We found that in live programming, customizability is actually really important. Programmers have different preferences for how much information they want displayed, and those preferences can vary even based on the problem they're currently trying to solve. So having a way to quickly customize a display really helps with being able to manage the tsunami of data that comes when you display all the data all of the time. But now, enough about projection boxes. This talk is not just about live programming. This brings us to chapter 2. Then came PBE. So programming by example is a paradigm where a programmer gives input-output examples and a synthesizer generates code from these examples. For example, you might say something like f of 2, 3 equal to 2, and f of 5, 8 equal to 5, and f of 9, 3 is equal to 3. And if you look carefully, these examples really are examples of the min function, and a synthesizer can figure this out and generate the code for you. Now in this case, what I'm showing you here, it generates a call to some built-in min function. But you can imagine that maybe if the min function were not available, a synthesizer could be smart enough to generate the conditional needed to implement min. Now, one of the benefits of programming by example is that examples are easy to understand. And because these examples use concrete values, they're essentially expressed in the language the programmer is already used to programming in. So in essence, it's easy conceptually for a programmer to know what they're supposed to do here. Basically, they just give it concrete examples of what they want. But still, nonetheless, examples require a lot of effort to express. So while it may not be hard conceptually, it still can be really, really tedious. And so here's where some of the cool stuff will happen. We will basically combine live programming and programming by example. And so just to summarize where we're at, we have live programming, which continually displays runtime values, and programming by example, which produces code from example values, but the example values are tedious to express and specify. So we see this opportunity for combining the two. And so the idea is that live programming can provide sample values for which to provide output, which makes it easier to specify examples in programming by example. And programming by example can then in turn extend live programming with the ability to generate the next code snippet. And we implemented the combination of these two ideas in a tool called Snippy. And let's see what that looks like with a demo. All right, so the example I'm going to show you here with Snippy is implementing a function called abbreviate that takes a name, for example, Alan Turing, and returns the initial separated by a dot. For example, in this case, a.t. And the example I'll be doing it on is the name Augusta Ada King. So here I'll take 3 steps. First, I'll split the name into words, then get the first letter of each word, and then put dots between them. So here I'll compute a variable called w, which is going to have the words in it. But instead of actually computing and writing code for it, I'm going to basically put question mark, and that's going to create for me a projection box where I can actually edit the value of W. So I can say what I want W to be. Okay, so what we want here is we want to enter the list that contains a string Augusta, then Ada, and then King. And now I'm going to stop for a second. I want you to pay attention to line number 9, because as soon as I press enter, it's going to go very quickly. So I'm going to press enter now. And you see how it actually generated exactly what we wanted, which is basically to split the name into words. Then I need the first letter of each word. So here what I could do is type W question mark. And what it does here is it pre-populates for me my F with basically W. That way I don't have to type in everything from scratch. I could just edit this. I could say, oh, what's the first letter of each word? So I could just do it like this, press enter. And then here I have the code for it. And finally here I need to get the result, which is basically, in this case, what do I want it to be? A.A.K, provide the example, and you can see how Snippy was able to do it really quickly. Now, it turns out that in this particular case, Snippy is able to do the whole thing in one shot. So we can actually remove all the code. So I'll just put a return here with 0. So I can basically do the abbreviate in one shot. So I'll basically provide one example here, A.A.K. And it's going to think a little bit. It takes a little bit longer than the other cases. And you can see that it actually was able to figure out all in one shot. That is the code. And here now I finally need to return that variable. And there you go. So that was a very, very short demo of how Snippy can enable you to write code by modifying the values in projection boxes to provide examples. All right, so let's see what we learned with Snippy. So we ran a study with 13 participants, and we asked the participants to answer several questions on a Likert scale. And the response was mostly positive. In general, the participants responded that Snippy was easy to use, and that they would like it to be available when programming. In other words, it's available, but you don't always have to use it. You just pick when you want to use it. In the same study, we also compared Snippy against using just projection boxes. So projection boxes by itself, no Snippy, but with internet searches. And we found that internet searches and Snippy complemented each other well. Snippy was more limited in what it can do, but participants mentioned that it could find solutions more quickly without the cognitive burden of switching to another program like a web browser to search for things. And that it could also find more compact solutions. Now, another thing we found really affects the usability of our synthesizer, and Snippy in this case, is the gap between the synthesizer's capabilities and the human's perception of the synthesizer's capabilities. So to better understand this, I'll plot here an axis that expresses the capability of the synthesizer with not very capable at all on the left, all the way to very capable on the right. And so any given synthesizer is going to be somewhere in the spectrum. So let's say we put it right in the middle here. And I'll make this box a little bit smaller just to make room for other things. What's interesting here is that programmers will have a mental model of what the synthesizer's capabilities are. And that mental model rarely matches reality, especially when programmers start using the synthesizer. And so this gap here between the actual capabilities and the perceived capabilities of the synthesizer is what we call the user-synthesizer gap. And we found that this gap really affects the usability of the synthesizer. So here in this diagram, the programmer is overestimating the synthesizer's capabilities, in which case the programmer will uselessly try things that never have a chance of working. On the other hand, the programmer might underestimate the synthesizer's capabilities, which is what's shown here, in which case the programmer will just not choose to invoke the synthesizer enough because they think it's not going to be able to help them in this particular case. Now, one really interesting finding of our work, which I think is a really good takeaway here, is that reducing this gap, reducing this user-synthesizer gap, is a really interesting and fruitful direction for future work. It's something that can really help make synthesizers for general purpose programming more effective. Finally, this brings us to chapter 3. Here comes the loop. So it turns out Loops are actually difficult, and that's not surprising. And to see what the problem is, let's go back to Snippy and try a loop out. So I'm going to try to use Snippy inside of a loop here. And so here I'm going back to the average example that I had at the beginning of the talk. I'm calling average with the list 1 to 5. And inside the code, I'm at the point where I need to write the statement that's going to increment s. S is the variable that's going to store the sum of all the elements of the list. So here, this increment statement is actually pretty straightforward, but I'm going to try to get Snippy to synthesize it. So I'm going to say s equals question mark, question mark. And now I can provide examples for multiple iterations. So I can basically provide an example for each iteration. Let's say here after the first iteration, s is 1. After the second iteration, it's 3. And after the third iteration, it's 8. And now I'll let the synthesizer work for a little bit. And you can see that what it synthesized is completely the wrong answer. And if you gave more examples, it would just not help. So one of the things you'll notice actually is if you look at what it synthesized here, it doesn't even use the variable s. Well, it turns out that in Snippy, the synthesizer is not aware of the variable for which it is trying to synthesize an expression, in this case s. Now of course we can tell the synthesizer that the variable s exists, but this brings up a much bigger problem. We now need to have values for s in the input part of each provided example, which is not easy. Indeed, when we are specifying examples, we had not synthesized this statement yet. And in general, we had not finished writing the loop. So the value of s when we were providing examples was incorrect. It was still 0 throughout. And so all of the examples we would be providing to the synthesizer would have s being 0 on the input part of the example, which is completely wrong. So now let's go back to the slides and better understand this problem and see how to solve it. So the first problem with loops is that values of loop variables in projection boxes are not correct until you write the entire loop. The case I showed you with summing up the elements of a list is the simplest possible case, but in general you can have many loop variables, and until you write the entire loop, none of them have the correct values for a programmer to use for specifying examples, which kind of defeats the original purpose of combining live programming with programming by example. Remember, we wanted projection boxes to allow the programmer to only have to specify the output of an example, not the input. The solution to this problem is something we call live execution, which runs a loop body each time a new example is provided. So let's see what that looks like. All right, so we are now going to try again what we were doing before, but this time with live execution. So here we have the average function, and again, I'm at the point where I need to write this statement that's going to increment s by the value x. So now I can say s equals question mark, question mark. And now what you'll notice is immediately this projection box looks a little bit different. Now we have s in and s out. And this reifies the idea that in fact there's two values of s. There's the value of s before this statement, which is really the value of s that came from within the loop iteration. And then there's a value of s after this statement. And so here we have, for this first example, we have that s out is going to be 1. And when I enter this, you'll notice that right away, the value of s in on the next iteration becomes 1. Then I'm going to enter here 3, and when I go to the next line, it'll basically have s in is equal to 3, and then finally I could put 8 over here, and now the s in and the s out are properly separated, and now I get the synthesizer is able to immediately generate the increment of s with x. Now in this case it was really simple, but in general actually you have to basically run the entire rest of the loop with whatever Python statements are already in there to basically figure out what essentially the next value of s is going to be in the next iteration. And that's really what live execution does for you. Okay, so now we are in better shape, but there is a second problem with loops, which is that synthesizing an entire block of statements is difficult to do at interactive speeds. I don't have time to show you a full motivating example and go through all the details, but our solution is an approach that can do block-level synthesis, including mutually dependent statements and top-level conditionals at interactive speeds. The key technical insight is a data structure called an intermediate state graph, which essentially allows us to efficiently explore different ordering of assignments in a bottom-up enumerative search. We have an OOPSLA paper on this called Interactive Program Synthesis with Control Structures, and I encourage you to go see the talk for that. And with all of this together, we get a tool called Loopy, which subsumes Snippy, and here's an example of what it can do. Okay, so in this example, I'm trying to implement a simple compression where repeated characters are placed by a number followed by the character. So for example, AA, B, C, 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 A gets replaced with 2A, 1B, 3C, 1A. So we start by setting up several variables. RS will accumulate the result string, last will be the last character we saw, and count keeps track of how many times we saw this last character. So next, we loop over all characters in the original string. And to generate the loop body, we are going to use Loopy. So we give examples simultaneously for all loop variables. I'll speed this part up a little bit, so don't worry about following all the details. It does get a little tedious, and I'll talk later about the issues with giving so many examples. But in the end, we get the code, and here you can broadly see how it works. Basically, count keeps track of the number of repeated characters we see. If the last character is the same as the current one, we increment the count. Otherwise, we add the count as a string and the last character to the result string and reset count and last. This gives you a sense of what Loopy can do and what kind of interaction model it has. So what did we learn from Loopy? We ran some experiments with Loopy, and I don't want to bore you with all the details, but broadly, Loopy handles a wide range of synthesis tasks at interactive speeds, and its interaction mode is usable. The more interesting part, though, is we found out that as the number and complexity of the examples go up, it is extremely important to have a more tightly integrated synthesis workflow. Just to start, if the synthesized code is not what you want because you didn't give enough examples, or maybe you made a small mistake in your examples, currently you'd have to start providing examples from scratch. Instead, you really want to be able to refine your examples quickly and then immediately see how it affects the synthesis. More broadly, you might actually want to co-design the synthesis algorithm with the user interface to provide a fluid and continuous mechanism for the programmer to incorporate synthesis in their work. Finally, we get to the last chapter, what does the future bring? In fact, I tricked you, actually, because I've been talking about the future all throughout the talk. In fact, I already mentioned 3 key areas of future exploration that can have a really big impact. Enabling customizability in live programming, reducing the user synthesizer gap, and more tightly integrated synthesis workflow. But I want to add one more challenge that is really important to address if you want to make interactive synthesis tools more usable. And that is helping programmers quickly and accurately comprehend code produced by the synthesizer. When programmers don't understand generated code, they may be less likely to trust it and adopt it. But more importantly, when programmers don't understand generated code, they cannot modify it, which means that only complete working solutions are useful. And unfortunately, this all-or-nothing mode of operation limits the applicability, utility, and potential impact of code synthesizers. So we see a great opportunity to use many different approaches, including live programming, to both help programmers understand synthesized code, but possibly even to guide the synthesis search to make the generated code more understandable. Before I finish, I do want to provide some links if you want to try things out. You should be aware that the online editor for projection boxes works best in Chrome and takes a while to load because it's actually loading PyDite, which is a Python stack running on WebAssembly. But the good news is that once it loads, all the Python code execution for projection boxes is actually happening in your browser, so there's no central bottleneck to worry about. For Snippy and Loopy, the same thing happens for running Python. However, the synthesizer does run on our servers, and so if too many people use it at once, it will slow things down. That's just something to be aware about. Okay, so that pretty much sums up what I wanted to say. I'm very excited about this research area. I think it's very rich and full of interesting directions. Lastly, I want to give a huge shout out to collaborators on this project. Not only would this work not have been possible without them, but they are such a wonderful and fun group to work with. So we have 2 PhD students, Khosrow Ferdowsi-Fard and Shraddha Bhark. Then there's Hila Peli, who is assistant professor at the Technion in Israel, and Nadia Polikarpova, an assistant professor at UC San Diego. So that concludes my talk. Thank you all for inviting me.